There's very important that all of your grounding electrodes be tied together. For example, your water pipe, all your utilities tied together, including gas. Though a gas line can't be used as a grounding electrode, it must be connected to the grounding electrode system such that during a surge, a lightning event, or a ground fault event, you don't have differences of potential that can affect the operation of your power system or create different voltages such that current flow to cause arcs, sparks, damage, injury. Such that a grounding electrode conductor, be it a ground rod, a ground ring, water pipe, all have to be connected together via low impedance path, and they must be maintained. Grounding electrodes are not permanent. They are not going to be forever. Everything on this planet is in time. Everything is in time. Consequently, it will pass and become deteriorated over time. But I'll use the example of a ground rod as a classic example. A ground rod is nothing more than a smooth piece of rebar steel, that's either been copper cladded or copper flashed. A copper flashed ground rod is one that's got 4 1,000ths of a layer of copper on it. And copper clad has 8 1,000ths of an inch of copper on the outside of the steel. Be it a copper clad or a copper flashed rod, and what you're seeing a lot in the industry is copper flash rods because they're less expensive and they're being imported that way, is if you take a ground rod and you drive it into the soil, there's a high probability that you're going to strike something solid as you drive the rod, say like a rock. And it doesn't take much effort or energy to scrape or damage the copper that's on a ground rod. Consequently, over time, the steel of the rod is going to be exposed to the soil and it's going to rapidly deteriorate. Ground rods do not last forever in the soil. On average, they are pretty stable for about 5 years, and after about 5 years, on average, depending on where they have been driven in the United States, they rapidly deteriorate. If you have a grounding system that's made up of ground rods and it's over 10 years old, you can pretty much be guaranteed that most of your ground rods are not near the shape they were when they were first installed. This is one of the reasons grounding electrode systems and grounding systems have to be inspected and maintained and often supplemented over time. Because as they deteriorate, so does your reference to earth, such that you thought you had a solidly grounded electrical system can become a low resistance grounded system, or worse yet, a high resistance ground system relative to the earth. Or your effective ground fault return path no longer exists in a bonding system. Bonding systems require maintenance and inspection on a regular basis also. It actually keeps us gainfully employed from time to time because these systems are not poorly maintained. We often find them deficient and offer recommendations and enhancements to them. We recommend that our customers inspect them on a regular basis, but it's called out of sight, out of mind. It's driven in the earth. You don't realize it's deteriorated or not there until you need it. And usually when it's found that it's deteriorated or inadequate is after an event has occurred. Or your overcurrent protective devices or your ground fault protective devices did not operate as designed and intended during a phased ground fault or during a surge event from a direct lightning strike, indirect lightning strike. You had no adequate protection. The other one I want to talk about is the equipment grounding conductor. The equipment grounding conductor is a conductor that's used to connect between the grounding electrode system and the device to be protected. For example, the equipment grounding conductor is the conductor that's used in a conduit, for example, to go between your electrical service, which is referenced back to your grounding electrode system. It is the path that is taken for the ground fault current, the majority of it, to go back from the point of the fault back to the service equipment as a means of getting back to the supplying transformer. Now, we mentioned earlier in the presentation, we talked about those 5 reasons for an effectively bonded and grounded system. We said that one of the principal reasons was that the ground fault current can flow in a relatively controlled path. The grounding electrode conductor that's employed in your conduit is that relative control path. It provides you a conductor, a direct connection between the equipment and back to the service. However, it's not a direct connection in many cases. For example, you start out at the service equipment and you have a grounding conductor that's associated with your feeder circuits that go out to, say, a dead front switchboard or power panel. And from a dead front switchboard, you might go to a motor control center. And from a motor control center, you go to a motor control center bucket or cubicle. And then from that individual cubicle, you would feed a motor. If we use the example of a motor having a winding that is shorted and went to the frame of the motor, we have to think about the return path, that ground fault return path between the frame of the motor and the source of the power, which would be the supplying transformer. Now, between the frame of the motor, there's an electrical connection that goes back to the motor control center bucket, that goes back to the motor control center, which goes back to the dead front switchboard, that goes back to the supplying service entrance equipment, that goes back to the supplying transformer. At each case, there are electrical connections that are made that add impedance to the ground fault return path. But by using a grounding electrode conductor, even though you are changing the size at the points through a connection to a ground bus, hopefully, an effective connection to a ground bus, you are trying to maintain a low impedance path between the point of the fault and the supply. However, what happens if, as allowed by the code, there is no grounding conductor in the conduit? What happens if the conduit is being employed as a ground fault return path? It's quite legal and allowed by the code and is often used in many, many installations. It's a relatively inexpensive means to provide a ground fault return path. The problem that arises is that the conduit is often employed inside facilities as EMT conduit, or it could be a rigid metallic conduit through couplings. But the conduit joints can actually rust over time or become loose. And as they become loose or rust in the joints, you add impedance in the return path, and that affects the operation of your overcurrent protective devices. Of more importance is most electrical conduit installations inside facilities, specifically data centers, use a type of conduit called EMT, electrometallic tubing. And the most common type of connection between electrometallic tubing are set screw conduits. All the conduit is installed at the ceiling. Most of the vibration in a building is at the ceiling. Most of the heat in a building is at the ceiling. Most of the moisture in a building is at the ceiling. If those connections become loose, rusted, or corroded, then you've actually added impedance in your ground fault return path that can affect the operation of your overcurrent protected devices as well as your ground fault protection system. But how often do people inside data centers get in a jig lift or a ladder or a scissor lift and go up and actually connect them? In my experience, just at random, I've gone into many, many data centers, well over 100. I've only found 2 in 30 years that were effectively bonded and grounded. Only 2 in 30 years of all of the data centers I've been in. On average, I find between 15 to 20% of the set screw couplings are loose when they're used as ground fault return path. Those are common issues we won't get into in the course of this video, but I did want to talk about the grounding electrode conductor. And I want to talk about the system ground conductor. The system grounding conductor, we said during a presentation the number one purpose in an effectively bonded and grounding system is to stabilize the system voltage. The system bond jumper is that electrical connection between the XO of the supplying transformer or generator or the output of the UPS and earth. It is what stabilizes the system voltage, allows for the 3-phase 4-wire center point of that Y-connected power system to be stabilized and connected to earth. Its primary purpose is to stabilize the system voltage, be it 480 volt